A bolted rail joint looks simple. 2 fish plates, a handful of bolts, and the rail ends are connected. But bolted joints are one of the most maintenance-intensive features on the railway. They work loose, and they can break, endangering the trains that travel across them. The common assumption is that bolts only work loose because of vibration. Trains pass over, things shake, nuts loosen. And that's part of it, but not the whole story. I've put together the 6 distinct mechanisms that reduce the force holding a bolted rail joint together. Understanding these will give you a grasp of how a rail joint behaves, why vibration alone isn't the issue, and what can cause a perfect looking joint to be less effective than it was intended to be. Before getting into what causes this loosening, how does a bolted rail joint actually work? Railway fishplate bolts are there to clamp, not just to connect rail ends. When a bolt is correctly tightened, the bolt itself is placed under tension. That tension pulls the fishplate tight against the rail, and it's that clamping force, that friction between the plate and the rail, that controls how the joint behaves when put under load. The bolt isn't carrying the wheel load directly, it's the clamping force that's doing the work. This force resists the tendency of the rail ends to move relative to each other. It controls vertical movement and keeps the joint stable as trains pass over it. It's not just the force of trains that bolted joints need to withstand either. In a well-maintained section of jointed track, as the temperature changes, all of the joints should close and open to the same extent. The temperature at which all the joints are closed up, with no gap between the rail ends, is known as the joint closure temperature, or JCT. Once all of the joints are closed, then the thermal stresses are shared across the distance of that jointed track, which can sometimes be up to several kilometres. When a bolt works loose, what's actually happening is that the clamping force on the rail end is being lost. As that reduces, the fish plates exert less force on the rails. The joint can begin to move in ways it shouldn't, and that movement tends to make the problem worse over time. Before we get to the 6 causes, a word from the sponsor of this video. Bolted rail joints depend on clamping force. Once that force is reduced, the joint can start to move, and once the joint starts moving, loosening just becomes self-reinforcing. That's why locking performance matters in rail fastenings. This video is sponsored by Stay-Tight, who supply fastening solutions used across the rail industry. One of their key products is the Hardlock Nut. The Hardlock Nut uses a 2-part locking system, with a lower nut and an upper nut working together through a wedge principle. The aim is to resist loosening from vibration and external forces, exactly the kind of conditions railway fastenings are exposed to regularly. Hardlock nuts are used in railway applications including track, fish plates, points and crossings, signalling, infrastructure, and rolling stock. So, while a locking nut does not remove the need to manage the joint as a whole system, it directly targets one of the key risks in this video, keeping the fastener secure when the railway environment is working against it. You can find out more through the link in the description. The 6 causes that lead to bolts loosening. Let's get into them. The first, and as I mentioned in the introduction, the one most commonly thought of as the complete explanation, is vibration. Every train that passes over a bolted joint sends vibration through the rails, into the fish plates, and through the bolts and into the nuts. Depending on the traffic level on that section of track, that can add up to hundreds of thousands of loading cycles over the lifetime of a joint. Vibration is a known challenge for threaded fastenings across many industries, and the railway is no exception. It works against the friction that keeps the nut in its tightened position on the bolt. But it's worth being precise here, because vibration is often used as a catch-all explanation. On a well-supported joint in good condition with a correctly installed fastener, vibration alone is not necessarily enough to drive significant loosening. Joints are rarely subjected to just vibration. Often, some of the other causes we're about to cover also factor in. Vibration is the mechanism most people think of first, but it's usually working alongside something else. The second cause is still related to vibration, but there is a difference and it matters. A bolted rail joint is a discontinuity in the rail. That means a point where the rail surface is interrupted. In a joint's case, there is a gap between the two rail ends rather than a continuous length of steel. This gap leads to a change in stiffness at that point, and when a wheel rolls over it, the load doesn't transfer smoothly. It concentrates at that point and the joint flexes in response. This is the whole joint being loaded, flexed and disturbed with every wheel passage, not vibration of the fastener assembly. The rail ends can dip. The fish plates can work against the bolt. The contact conditions between the plate and the rail change under this type of loading. This is where a deterioration cycle can set in. If the joint has poor ballast support beneath it, or if the rail ends have started to batter, joint movement under load increases. Increased movement reduces clamping force. Reduced clamping force allows more movement. The joint degrades faster than the individual causes would suggest on their own. Dynamic loading at the joint is one of the primary drivers of why rail joints are harder to maintain than continuously welded track. The joint is inherently a weak point, and the load behaviour at that point is working against the fastener and the rest of the joint from day one. The third cause, and this one is easy to underestimate because it's gradual and often invisible. Over time, following installation, the components of a bolted rail joint bed in. Surfaces that were in full contact when the joint was assembled start to wear or fret under repeated loading. Fretting is wear caused by repeated small movements between surfaces that are in contact with each other. Rail end faces, fish plate contact surfaces, bolt holes, all of these are subject to small changes over time. The consequence is that the clamping forces reduce even if the nut hasn't visibly moved. You can look at a joint and see that the nut appears to be in the correct position and still have a joint that is significantly underclamped because the surfaces it was clamping have slightly changed shape or lost contact area. Fishplate wear, rail end batter, changes in support stiffness, deterioration of the contact faces. All of these reduce effective clamping without requiring the nut to rotate at all. This is one of the reasons why checking whether nuts are present isn't sufficient. The joint needs to be assessed as a whole system and not just inspected for obvious defects. For the fourth cause, we have thermal movement and the behaviour of the joint gap. Rails, like any metal, expand when they're warm and contract when they're cold. What's worth focusing on here, specifically in the context of bolted joints, is what that movement does to the joint itself. As we covered earlier, some bolted joints have a gap between the rail ends, by design, to accommodate thermal movement. As rail temperature changes, the rail is trying to expand or contract along its length, and the joint sits in the middle of that movement path. That longitudinal movement loads the bolt in directions it wasn't primarily designed to resist. It works the joint, affects the contact conditions between the fish plate and the rail, and if the joint gap isn't set correctly, or if the bolt holes are elongated over time, the range of movement that joint experiences can increase. Joint lubrication matters here too. A dry, corroded joint transmits thermal movement differently to one that's been properly maintained. A bolt is dealing with forces from rail temperature every time conditions change, which in the UK, for example, can mean significant daily and seasonal variation across the lifetime of the joint. The fifth cause is corrosion and general condition deterioration. Railway bolts live in a hostile environment. Water, mud, ballast dust, chlorides from de-icing, general contamination. All of these attack the bolt, the nut, and the other joint components continuously. Corrosion damages the threads of the bolt. It reduces contact quality between mating surfaces. It makes reliable tightening of the bolts harder because the torque being applied no longer cleanly translates into clamping force in the way it would on a clean, properly prepared joint. There's also a hidden problem. A joint can look assembled, bolts present, nuts on, fish plates in place, and still be generating clamping force well below what the tightened nut suggests. Heavily corroded contact surfaces, damaged threads, or significant contamination buildup all reduce the actual clamping being achieved, even when the rail joint looks good. from a distance. Corrosion is a slow issue, but it's relentless, and it interacts with every other cause on this list. A corroded joint is more susceptible to dynamic loading effect, more prone to movement, and harder to recover through a maintenance intervention alone. The sixth cause is different to the previous 5. Those first 5 are all things the railway environment does to the joint. This one is what maintenance, or even initial installation, can inadvertently do to it. When a bolt is identified as loose or being installed for the first time, the correct thing to do is tighten the bolts. How this is done ranges from impact wrenches and powered torque wrenches right through to manual torque wrenches, and the method used matters. The order bolts are done up in also matters. The correct order to tighten bolts is 2, 3, 4, 1, done twice. Not tightening the bolts in this way, such as tightening each one up fully on the first pass, has been shown to give up to 30% variability in clamping force in each bolt. Powered torque wrenches and impact drivers introduce a specific risk. These tools can deliver torque rapidly and in high volumes, but accuracy of them is often low. If the applied torque exceeds the design limits for the bolt itself can yield. Once it's been stretched beyond its elastic limit, it no longer behaves as intended. It cannot maintain the clamping force as it was designed to provide, even if it still looks good and in position. The result is that a joint appears to be correctly maintained, but again is actually underclamped. The bolt is there, the nut is tight, the clamping force is just not what it should be. There is a second specific risk to the fish plates themselves. Over-tightening doesn't only damage the bolt, excessive torque can initiate crack failure in the plates. In the early stages, those cracks can be difficult to identify in size. The size of the crack, dirt, and the general condition of the joint can all obscure a developing crack during inspection, but left unaddressed, a crack can propagate. If both fish plates at a joint fail, the joint can no longer perform its structural function, and in track terms, that condition is treated as a broken rail. Fish plates and their bolts are designed to do a job, but they need to be installed, tightened, and maintained correctly. The common practice of tightening bolts up as far as possible with no thought about torque is a common way maintainers harm joints they were supposed to be fixing. Take all these 6 causes together, and it becomes clearer why bolted rail joints can be a challenging maintenance problem. It's worth noting that railways have been moving towards welds as the primary way of joining rails, precisely because it removes joints, but in places, bolted joints need to remain, so the challenges stay. Remember, the joint itself is a discontinuity in the rail. It carries repeated, concentrated wheel loads at a point where the rail is already interrupted. It's subject to vibration, thermal movement, contamination, and weather exposure continuously. Its components wear and deteriorate over time, and this leads to a level of constant maintenance intervention needed to keep joints in good condition and performing properly. Each one of these issues on its own is very manageable, but they don't act in isolation. They interact. A corroded joint with worn contact surfaces in poor ballast support being over-tightened with power tools without torque control. That's not just one problem, it's a number of factors compounding each other, which can make joints a maintenance headache and in need of constant attention. The bolt is one component in the joint and in the overall track system, and the system is under constant pressure from multiple directions at once. So, what actually happens to a joint when loose bolts are left unaddressed? The joint starts to move in ways it shouldn't. Rail end batter develops, the ends of the rails begin to deform under repeated impact loading as the wheel hits the unsupported rail end. This batter increases the impact load at the joint, which accelerates deterioration further. Fish plate damage follows, and the joint is moving. A joint that's moving is a joint whose fish plates are working against each other and against the bolt, accelerating wear on the contact surfaces and the bolt holes. Track geometry deteriorates. A joint that isn't properly controlled contributes to both vertical and horizontal geometry faults. Those faults generate higher dynamic loads, which worsen the joint condition still further, and the rate of deterioration accelerates. A joint that developed significant movement doesn't respond to tightening in the way a well-maintained joint does, because the underlying conditions of the components has already changed. 6 causes: vibration, dynamic loading, settlement and wear, temperature movement, corrosion, and over-tightening during maintenance. What connects all of these is clamping force. Every one of these mechanisms either reduces the clamping force the joint was designed to hold, or prevents it from being correctly restored when maintenance is carried out. The visible thing, the loose nut, the backed off bolt, is the end result of a process that usually has been developing for some time, and that often involves more than one of these causes acting together. Railway bolts work loose because the joint, the fastener, and the surrounding track conditions can start working against the clamping force that's holding everything together. Understanding that is the starting point for maintaining bolted joints properly. If you want to go deeper on joint components, what they do, and how to identify them on site, my track components guide is free and it's linked in the description.